Hey, welcome back. Today we're going to be talking about an AP Physics C Mechanics FRQ, and it's from 2011. It's number 2, and it actually has some really important ideas to review, primarily dealing with forces and energy, but there's also a differential equation embedded in it, so it's good practice for any AP Physics C Mechanics student. So let's go ahead and get to it. I'm going to try to refrain from reading at you this wall of text here. So if you could just take a look at this, you might want to pause the screen and read it. I'm just going to highlight a couple things here. One is that the track is frictionless. That's important. And for A, we're being asked to draw the forces. So notice that they're saying not components. That's important here because later we will be drawing components. But if you take a look at position C, so this is what they're talking about for right here. If you think about the forces, remember you're going to have a normal force. That normal force is going to be perpendicular to the surface. And of course we also have gravity as well. So that's going to be our Fg over here. And that's it. Those are our two forces. So let's move on and take a look at part B. Okay, and so for part B it says in terms of theta and the magnitudes of the forces, determine an expression for the magnitude of the centripetal force acting on the compartment at point C. And very good. So let's think about this. So we would say the sum of the forces. Now in this axis, I'm going to call this direction in. So let me show you what I'm talking about here. This is our normal force right here. This is our force due to gravity. We do know a couple other things that are going on here. We've got this dotted line that is at a right angle. I could draw this dot representing the object. We also know that this angle is theta right here. So this angle is theta. Notice I'm drawing this as a separate drawing from what they had asked me to draw in A because I'm going to do something with this right here. So notice we've got our theta right here. We also have a theta right here. So this is alternate interior angle. Well, we're going to have to relate this somehow to the force due to gravity. Let's think about this. We go down here, we could say if we draw an angle kind of like this, this would be the same as theta. So then what would this angle, this theta, be down here? Well, this would be the complement of theta, right? If we think about our FG, we draw our FG over here. In other words, we need to relate theta somehow to Fg eventually. This is Fg right here. If this is theta complement, now we don't know what theta is. Theta is a variable, so we want to put things in terms of theta. So how could we use theta and this triangle here? Well, one way we could do that is to say, well then this angle right here would be theta if we're dealing with the complement right there. So, and instead of using x and y, I'm going to call this the direction in, and this negative direction is the direction out, so to speak. So we could say, what do we know? Well, we do know that this is Fg in right here because the problem set asked us to come up with the centripetal acceleration. So if you've listened to my videos previously, you know I like to do something called the sum of the forces strategy. What we're going to do is add up the forces that are in the axis we're dealing with. So in terms of the forces in, we're going to have the normal force, and in terms of in the same plane, we've got a force out, so to speak. So this is the force due to gravity out component right here. The second line for the sum of the forces strategy is just going to be mass times acceleration. And when something's moving in a circular path, normally I would say, oh, we're going to make this centripetal acceleration, and we can throw in Vt squared over r for centripetal acceleration. This is all just what we would typically do, but here we're not going to do that. We're actually going to summarize this, and we're just going to label this and just call this force centripetal. So this right here is what we're talking about with our centripetal force. We don't need to break it down any further because the question is asking about the centripetal force. So we could just say, all right, let's set these two equal to each other right here, these two equations. So we could say force centripetal is equal to Fn minus Fg out. Well, what do we know about Fg out? All right, well, we know Fg, this is equal to m times g. Actually, I'm going to make this a capital M because in the problem they want us to use capital M. And this is in, out in this case. So I'm going to change this up and just say, what would Fg in or out be? Well, what that's going to be is mg times the sine of theta. Now notice we're putting this in terms of sine of theta because we have theta. We don't have the complement of theta. It's actually just going to be easier to do the problem this way too. So this is essentially going to be the answer for part B. All right, next up, I'm going to move this down so we can take a look at part C and think about what we have. So it says derive an expression for the speed v sub d of the passenger compartment as it reaches point B in terms of capital M, R, and fundamental constants as appropriate. So there's no collision here. I'm not thinking in terms of momentum. There is a change in height or conservation of mechanical energy, particularly because it did say at the beginning of the problem that there was no friction to be aware of. So we're going to think of this as a conservation of energy problem. We could say the sum of the energy at part A, therefore, is equal to the sum of the energy for B, is equal to the sum of the energy for C, is equal to the sum of the energy for D, mechanical energy. What we could do with that is let's pick the two that we need to pick. In other words, the one that we do need to pick is going to be point D because the problem tells us that. But also, out of A, B, and C, which do you think would be easiest to get information about the total energy that's in that point? Well, A is going to be the easiest to work with, right? Because A, I believe this starts from rest. A starts from rest, meaning it doesn't have kinetic energy to begin with, but it does have potential energy to begin with. So we can set these two things equal to each other and see what happens. So we're going to say mgh is equal to 1/2 mv squared. Okay, couple things to note. One is we need to start thinking about what our h value is. So take a look at the diagram for a moment and see if you can figure out what the h value is going to be going from A to D. Okay, well they tell us in this part of the equation right here we've got 3/4 r, and this will go down a radius as well. So in terms of the height difference between A and D, we've got 3/4 r. Let me write this out in case I throw anyone off. So we could say 3/4 r plus an r, right, is equal to 1/2 mv squared. All right, notice immediately that the m's go away as well. Let's simplify that now. Let's think about what's going on with our r. Well, if we want to get common denominators here, this really is going to be 4/4r. It's the same thing as 1r, right? So that means we could say g times 7/4 r is equal to 1/2 v squared. And the question asks us to derive an equation for Vd. We could label this as Vd and go back just to clarify what we're talking about. Alright, to get rid of the 1/2 on the right hand side, let's multiply both sides by 2. I'll bring out the 7/4 out in front, so we have 7/4 times 2/1 times g times r is equal to v sub d squared. And simplifying this, we're going to get 14/4 times g times r is equal to vd squared is equal to vd squared. And lastly, we could say Vd is equal to the root of 7/2 gr. Alright, so that's going to be our speed at position D. We're going to box that for now. That's our answer to part C, but that's also going to be useful later on. Typically, the way this works in AP Physics E Mechanics FRQs is when we solve for something, we're almost certainly going to build on that and use that in a future part of the problem. Alright, so let's move on to D. Okay, and so D says a force acts in the compartment between points D and E and brings it to rest at point E. If the compartment is brought to rest by friction, calculate the numerical value of the coefficient of friction mu between the compartment and the track. So let's think about what's going on. We're going from D to E, and we know how much energy we're dealing with. We have some energy here. It's in the form of kinetic energy, so we could say the kinetic energy for part D is going to have work from friction put on it, and then you're going to have zero energy. In other words, all of the kinetic energy is going to be dissipated by work from friction, so the ground and the object that's sliding across the ground, those are going to heat up, basically, if we're dealing with friction in this case here. And one thing that should stand out, if you are thinking about this, is called the work kinetic energy theorem. And if you don't know this, this is something you're just going to have to memorize. So you could say work net is equal to the change in kinetic energy of an object. So that's not on your equation sheet, but it's important to note. All right, so let's think about this. We've got our kinetic energy at D is effectively going to be equal to the work done by friction. And so what is that? Well, our kinetic energy at D is equal to the force from friction times the distance over which that force is applied. It's going to be considered to be a constant force, so we don't need to use calculus to be able to solve this, and we don't need to worry about a cosine of theta function because the force due to friction is already pointing in the direction of motion. And what else do we know? Well, we know that this is 1/2 mvd squared, and this is the force due to friction would be mu k times Fn, right? And this D, what is this D value? Take a look at the diagram here and see if we can do something with this distance over which the force is applied. Well, in this case, that's going to be 3r, right? We want to put everything in terms of the variables that they give us if we have variables to put things in. Next, we need to start thinking about what Fn is. In this case, it's on a flat horizontal surface. This is just going to be m times g. I could prove that to you. I could use the sum of the forces strategy really quickly and let you think about this as we go from D to E. In terms of the y-axis, what are our two forces? Well, we say the sum of the forces in the y is equal to the normal force minus the force due to gravity. The sum of the forces in the y is equal to mass times acceleration of the y. During the time as you go from D to E, the acceleration of the y is 0. That goes away. You set these equal to each other. Fn minus Fg is equal to 0. Therefore, we can say Fn is equal to Fg. In terms of their magnitudes, they are equal and opposite to each other. And what is Fg? Well, that's going to be, usually we would write it as little mg, but in this case, we're going to be writing it as big mg, just to be careful and consistent with what they're asking us to do. All right, so let's fill in what we have here. mvd squared is equal to mu k times mg3r. Okay, so we're getting closer. Really important though, what I had mentioned for the last problem is we had solved for Vd. Now we need to bring that back. So let me grab that really quickly. Okay, and so this is what we had solved for Vd. Let's go ahead and plug that in over here and see what happens. Oh, and let's get rid of the masses before I forget. So we have 1/2, and then we put in this business right here, the root of 7/2 gr, and this whole thing is squared, which is handy because that means the square root is going to go away. Mu equals mu k times g times 3r. Alright, well let's apply that squared to the square root, so we end up with 1/2 times 7/2 gr is equal to mu k g times 3r. Now we can get rid of our r's, and we can get rid of our g's, and we should remind ourselves of what the question is asking of us. It's asking for this mu value, so let's solve for mu. Here, let me move this down a little bit so we have a little more room, and we end up with 7/4. To get rid of the 3, we're going to multiply by 1/3, and that will leave us with mu k, so we can say this is 7/12 is equal to mu k. That actually is good enough, like for our answer. That's pretty precise actually, so we could leave it as that, or if you just feel more comfortable, we could just call this 0.58 is equal to our mu k. That's how we would approach this problem. Remember, mu k is just a ratio of forces, so it's effectively unitless. Okay, let's move on. There are harder parts to this. Alright, so taking a look at E, it says now consider the case in which there is no friction between the compartment and the track, but instead the compartment is brought to rest by a braking force, minus kV, where k is a constant and v is the velocity of the compartment. Express all algebraic answers in the following terms. Those are given, and the fundamental constants as appropriate. Write but do not solve the differential equation for Vt. A differential equation means that you're going to have something like a velocity and also like the derivative of velocity in the same equation. So for part I, or part 1, I guess, whichever, you're going to say the sum of the forces in the x is equal to, specifically, minus kV. That's what they tell us it is. The second line for the sum of the forces strategy is just this, m times a. You set these equal to each other, and so you end up with minus kv is equal to m times a. This is always a safe way to start a problem involving forces. I call it the sum of the forces strategy. Okay, now they're talking about a differential equation over here. Like I said, that involves using like the derivative of one variable along with that variable in the equation. So we need to sub in something here. We know that a is actually just the derivative, so we could say dv over dt. We know that's the case, and they've asked us to just write but do not solve for this part. Okay, that's it. That's it. In other words, you'll get points just for doing this. Notice the last couple points on this FRQ are going to be the hardest, but just know that you can get a 5 without getting these last points here that I'm going to go over. So let's continue with this. For part II or 2, whatever you want to call it, it says solve the differential equation you wrote in part 1. So let's begin by rewriting this. And generally what we want to do is get variables on the same side aside from our constants. So we have a couple constants here. Oh, by the way, I need to go back and rewrite this as a capital M. I just do lowercase m out of habits, but for the College Board, just be careful with that. They do want to see it in terms of what they are talking about. So I'm going to go back and rewrite this as a capital M. Okay, so I do want to point out though that K and M are going to be constants. We're really looking at V and T, and we want to combine like the V's on one side and the T's on another side. So let's start by doing that. We could say, well, what if we take dt, multiply dt on both sides? If we do that, we end up with, okay, so this is easier to deal with, but we still want to combine our V values. So let's go ahead and divide both sides by v. If we do that, we end up with this. Alright, I did bring the m, the capital M, over to the left side as well. Minus k over m is a constant, so we don't need to worry about that so much. What we're going to do is take the integral now of both sides at this point. You can do that combining algebra and calculus, so to speak. If you take the integral of the left side, you have to do that to the right side. Let's think about what happens here. For the left side, you can immediately draw out the minus k over m and think about what the integral would be for dt evaluated from 0 to t. And on the right side, this is going to end up being the integral of dv over v. Now we know what we start out with. This is vd is what we start out with, and we end up with some variable v. Like, we're trying to come up with an equation that will help us to determine what the velocity is going to be at any given time. So that's what we're doing here. Let's go ahead and take this and work it up here and see what we can do. So this will be, and that's how we could begin to evaluate this. I need a little more room, so I'm going to zoom out and move over a little bit just so we can all see what's going on here. On the left side, this 0 right here is kind of irrelevant. Like, we could plug in a 0, but then it would be 0, so we can kind of forget about this. But this ends up being, and then on the right hand side, what we're going to do is, if you take the natural log of, say, v minus vd, that just becomes the natural log of v over vd right here. This is really crucial, this step right here. Again, if you don't get this point because your calculus is not as strong, that's okay, but this is how you would go about doing this. When I say that's okay, I think you can probably get a 5 on this FRQ without even getting this last. Now again, we want to get v by itself. So we want to get v, a function of v by itself. So how are we going to go about doing that? We want to get rid of this ln function, this natural log function. To do that, what we're going to do is, I could rewrite the equation, but effectively we're going to have e to this power. In other words, we could just say, we're going to make this whole thing as a power of e, so to speak. And if we do that, that cancels out. In other words, this will be canceled out. You'll be left with e to the minus k over m times t power. And then over here, you'll be left with v divided by vd. And remember, the question is, can we solve for this v value? This is really what we want right here. So we want to get rid of the vd. So all we have to do at this point is just multiply by vd. Both sides, of course, vd. That will cancel this, and just a preference thing, I'll write this on the left side. So this is going to be vd times e to the minus k over mt power. That's how you're going to solve for this part 2. That's how you go about doing this. And for the last part right here, they're asking us to plot the acceleration, not the velocity function that we just solved for, but the acceleration. So how would we get the acceleration function from this velocity function? Well, what we would do is need to take the derivative of that, right? So we could write out like a is equal to dv dt, and that would be helpful. So the derivative of our function right here, what you do is you take that power minus km are constant, so they come out in front. You have Vd times, and then what was left before, minus kt over m, you could say, and what they are asking us to do. So this is going to be our acceleration here. That's our function. And then it says, on the axes explicitly label any intercepts, asymptotes, maxima or minima with numerical values or algebraic expressions. One of the things we can do is say, well, like, what would be the acceleration at time equals 0? Well, if we do this, you think, all right, if we just take the value here at time equals 0, well, anything to the 0 power is just 1. So this whole business up here, I'm going to put in parentheses right there, that reduces to 1 at time equals 0. So if that's the case, at time equals 0, we could say our value is minus k over m vd. Okay. So we can write that. Let's go ahead and write that. At time equals 0, we've got some value of our acceleration is going to be, and they do say magnitude, right? So we don't have to worry about this negative symbol right here. We can just say k over m times vd. That's going to be our acceleration at time equals 0. So effectively, this equation is in the form of an exponential decay with an asymptote that approaches 0, but never quite reaches 0 here. So hopefully this has been helpful. I've done lessons on an entire year of physics as well as most of the ideas in AP Physics C mechanics. If you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.